Okay, welcome. Okay, so it's time we start our today class. Yeah, so yesterday we talked about the Suita conjectures in 72. Okay. You can compare two invariant matrix. One is Suita matrix, the other is Bergman matrix. So, and the conjectures is following inequalities that E to rho at any point z is less than pi k omega z. Okay, so this is a Robin functions, which is limit of green function minus 2 logarithm part when g go to the point, the pole. Of course, anyone can make any conjectures, but the conjecture we will conjecture if you have evidence, right? Otherwise, it will not be conjectures. So first thing is that if omega is simply connected, then it equal is identity. I mean, first you check it for disk, unit disk, because both okay, you have a explicit formulas, so it equal to identity. Okay, and then by simply connected as an exercise, but you can use a Riemann open mapping theorem, because both of these you can convert to that case. So this is identity. And he goes further in this paper by Suita that omega is the annulus for some r is bigger than 0 and less than 1. Then indeed star become a strict inequality. Okay. So at least this gives you a lot of evidence to suggest this kind of things. So he made the conjecture. Okay. That is true. So as I mentioned yesterday, that I mean people can live with this without the proof. But then when you reformulate it, okay, recall that k of omega at z, just you can rewrite by another way by take suffimum. Instead normalize the L2 norm, you divide it to the bit norm, such that you take all of f in our inverse space except the 0. So this is remote formalization of the Bergman kernels. So the star inequalities can be restated as follows. For xa, fixed point in omega. So which means that you have this and these values. So you keep the left-hand side fixed. So you consider the problem minimum the right-hand side. And the minimum right-hand side just what is. Then the equivalent to say that for x point A, there exist holomorphic functions. Okay, such that okay, you put A here, so you can fix is 1, and you ask how large this norm can be, which means that how small its number can be. Then you get the minimum, then you get the inequality, right? So such that two conditions. One is fa, as I said, equal to equal to 1, and because you keep the left-hand side fixed, and the L2 norms of f square will be less than just gen pi 2 over e through omega of a. So is it equivalent formulations of this conjecture. Right? But this is a different problem. Given a point in omega, can you find a harmonic functions which interpolate at that point value is 1? And the L2 norms is of this at most this norm, this value. So it called the extension problems in complex analysis. And because of, we notice that the inequality is sharp. So this norm should be the sharp estimate. Okay, so this is called the extension problem. This is extension problem in complex analysis. And this one called the with L2 estimate. Because you estimate the L2 norm. Okay. Okay, so instantly you related the Suita conjecture with very well-known theory developed in 1987 due to a paper by Ozawa and Takekoshi. So Ozawa, Takekoshi, in 1987, they obtained much more general versions. Of L2 extensions. I mean of this kind. But for several complex values, we will come to that at the very end of the lectures. And then they obtained the theorem with some constant. So it's not sharp. So these Suita conjectures equivalent to say that the other part of their theorems is the theorem with sharp estimate. So now people cannot happily live without the proof of sharp estimate because it's a huge theory and you wish to know what is sharp estimate. It's a problem a long time ago, not from beginning of this paper. Okay, so that's why people come back to think about the Suita conjecture. Good. So to solve this one, because it's not solved in 72 because there's missing ingredients in 87, 15 years later. But again, one of the, to solve this one, you have to, study a subproblem and 3 steps. So far we, okay. So there are 2 steps at least. Step 1, you have plenty of functions on the domain, but how to choose a good one? I ask you to construct a Hollow function with some properties, then it's difficult. You have plenty, but which one is good is for our purpose. For instance, we will come to that. To construct the Hollow functions with non-trivial properties. Or at least one of the property we are given. Then it's not easy, okay? Because all of the Hollow functions you know is just polynomials or this construction of all that kind of things, but you don't know what is property you have in hand. The second, that's first sub problem, and second, once you can construct with, with control, good control, then you can go to further to ask, okay, choose the good one, okay, extend. So we have 2 sub-problems. So because of the whole proof of Suita conjecture is beyond our course, so I just mentioned step 1 is a basic one, okay, in our course. So any questions? So now let me mention what do I mean is non-trivial properties. You know that given smooth functions in omega, okay, say complex values, then you know that this guy also smooth function in omega, right? So one of the main tools to construct the non-trivial Holm function is that you solve this one, say find a function h, smooth one, so that d over d g bar equal to f, this one, given, okay? So once you can find h, then of course you get that right? That's what I say, because now you can given any smooth function right hand side, you solve this equation, then you get some Holm function. At least you know some properties of h. That is basic first step I want to mention. Good. So again, given these problems, you also have to think, okay, now how can I do this? So first is the toy models. That case one, simplest one, just take omega, just a disk of radius r. Okay. Then later on, you can consider the general case. So for many reasons, the unit disk or the disk are the most pleasant example to in complex analysis. Okay. So, but there's very there are two cases, but they are very different. Okay. And because of lack of time, I just only mentioned the result for this one, which much quicker than the general case. Because to deal with general case, we need different idea. So for case number one, the disk. Then this was solved a long time ago. It also, I mean, part of the generalization of the Cauchy formulas for non-harmonic functions. Okay. Then, I mean, this one we can just, instead of write d over d bar of z, you could just take any smooth function, right? Instead of writing this one. So our goal to find given this one. So goal is given f smooth in omega with complex values. So can you find function h to solve this one? Okay. So theorem today is 4.1. Let f is smooth functions with complex values from D with values in C, and fix with smaller numbers, small r, and define the following function g of z equal to minus 1 over pi of double integral on this smaller disk f of w and w minus z, so dx dy, where w equal to x plus. So the variable is w, f is z is fixed. Okay, then the conclusion is that then z is smooth, and it solves these so-called D-bar equations. So-called and solved and satisfy the d bar equation, meaning that you have dz over dz bar equal to f in this smaller disk. So if you work a bit harder, you can show that it also solves this equation in our given disk, but the proof is a bit harder. And some remark is in place. So the right hand side here is well defined, okay? Because this smooth function is bounded. So when you take absolute values, so the singularity here at most is modulus of z, which is square root of the x squared plus y squared, and this double integral, so it converges. So the right hand side is well defined, okay? Because you need this z smooth, so at least this is well defined. And this is just double integral, as I explained earlier, for complex integral. You just separate f to be two parts, real part and imaginary part, and take double integral. Okay, that's two remarks. And the proof, I will just mention some step. I will not go over it because this just model case and give us a weaker result. We could go to the general case with a fundamental different idea. Okay, so this is a statement. And I mean, in the model case, we simply solve problem. But if you go through the proof, it's quite elementary, but very sophisticated computations. Use also so-called Green theorem. Then you discover that the proof uses two facts. One is symmetry of the domain unit disk. Or if you can remove the symmetry of domain, that require that the function on the right hand side should have compact support, which means that you avoid the boundary value. So prove this one. If you go through the proof, we will not go, but anyway. So now we go to the second case, which is still nowadays people use the method. So any questions for this special case? So if you know there's a so-called Cauchy formulas for just smooth functions, and there will be two parts. One is if you know it, but anyway. So the Cauchy formula, if one of you have seen it before, so you know that f of z can be written as 1 over 2 pi any disk, right? Just take 0, 1, say f z of zeta plus minus of zeta minus z. These are whole form functions, and plus with this guy, say d for general smooth function. So it goes so-called the general Cauchy formula. So that's why the boundary appear. So that's why if you go through the proof of this one, if you have the f is compact support, so this will be 0. So that's why the whole function is given by this formula. Okay, so this so-called the general Cauchy formula for smooth functions. So if f holomorphic fixed, so this part instantly Q. Okay, so know this part. So it's extra thing. It may be minus or plus here. Okay, so we will not go through proof it because of lack of time. So now we go to the second case, general case. But anyway, it's a very pleasant exercise to really compute the partial derivative in d over d bar of this function and to get that it equal to f in smaller. disk. It's very nice exercise. Okay, general case. So the general case was solved by Hochmanders. So general case, the ideas. Any questions? So it is due to Hochmander. Surprising that it is. Again, he solved for several complex variables. Okay, and we just introduced the idea in the one-dimensional case, and there's a lot of simplifications, and we have very nice picture. So, what is the idea? Again, we use the so-called functional analysis. Okay, let's the simpler situation. So let phi to be a now C2 functions. It's called subharmonic. So it's real value with the properties. Now you write it Laplace of, for convenience, I ignore the constant 4 to choose Laplace equal to d over d bar. Now strictly becomes 0. So it's subharmonic function. Okay. But Laplace should have 4 here, but I ignore this because it is constant. Okay. So then you introduce the following space L2 log of omega, a bit larger than the L2 space complex values, such that for any compact set, then the L2 norms of dx dy is finite for every compact set. Okay, so if, we have to extend a bit the function here so that it may just measurable, okay, because we consider it a measure, but if you are not have take any course in measure theory, just consider as just function, say continuous one maybe. And the idea why we have this one called the weight is following: the weight space. You see why later. L2 of weight is e to the minus 3 omega is the set of all functions in this space G okay, L2 log omega such that its L2 norms of Z with respect to this weight is finite. So instead of dx dy, we multiply with some weight constant here, some functions. So it's still, yeah. Then this new space also become the Hilbert space. This with the following inner product. Then, as previous case, L2. So we fix the domain omega, so we don't need to mention it every time. It's a Hilbert space. With the inner product with the following: as before, f and g equal to omega f z bar. But instead of taking against with the Lebesgue measure, now you consider with this weight. Okay, so there are a bit of singularity here because this guy smooth on the omega, right? So that's why we require it's locally bounded. in any compact set, then this is good. Okay. So to solve the bar equations, we need to first extend a bit the notion of solutions, not checking points-wise, but checking the solution in the term of, functional analysis, in terms of functional. Okay, so we define the following so-called solutions. Because this function just, very general function, continuous or measurable function, it's not necessarily smooth because our space just L2 space. Okay, so first we extend the notion of solution first. So given a function in this space, we say that d over e bar u equal to f, our star equations. In the weak sense, that's why it's called extension. It's not usual sense, but in the weak sense, if, because now you have inner product, so instead of checking this points y, you can looking at them as a functional. So by this equation, you say that, okay, when you take the inner product with other element, they give the same value, then you are good. Okay, if, so what I say is that u, the alpha over the z bar will be equal to f on the, for any alpha which is a smooth function with compact support in omega. For any alpha smooth and compact support in omega. So we often denote this space is C omega. Is clear? So why do I choose this? Because one of the exercise asks you to show the following formula for a smooth function. So f d over of 8 alpha will be equal to minus, I think should be minus, of 8 for any alpha in this space. Remember, it's complex value. So if generally you given a smooth function h, okay, then the values of d8 d over dz bar of 8, then it will equal to this guy, f, right? Right. So instead of looking at the value on this right hand side, I consider it as equal to, am I right? I think, yeah, equal to f f alpha, I think, yeah, f alpha here. F alpha. So this equal to f alpha, right? F multiplied with alpha. So this, if you solve this equation in the classical sense or usual sense, then it should be equal to f alpha. But the right hand side now is well defined because this guy is smooth, so this is well defined, and this function just only required to be in our. Okay, so this all the way well defined because this smooth and this. Okay, so then we take this to be the, definition of the this guy when you act on any compact smooth functions support. Okay. So if you have this inequality, so you call that you solve these equations, but in the quicksand, because you just need the actions, not real points-wise inequality. Okay, so we extend a bit our notion of solutions in the Hilbert space. So, I mean, every time something weaker is easier to find. That's the philosophy. So, any question for the definition of the weak solutions? Is it clear? So this one just come from integration by part. If this function is smooth, then it's equal to this value. But now this right-hand side always valid for just 8 in L2. So we pick this to be the value of this guy. But if you replace this guy, if it have solution F, then you put it F here. It means that if you have these identities every time for alpha is compact support, then you declare that d8 over dz bar equal to F, but in weak sense. So that is the idea of defining the weak solution. Okay. Then we also have the so-called weight product, because you introduce the weight phi inner product in the L2 log, and now you also introduce I think this one already. Yes. Yeah. So it should be here, because it also related with phi. So sorry, I should write it already. Yeah. Okay. Good. So a bit functional analysis. You define the following operators. Define. Looking complicated, but let me write it first. For alpha, remember alpha is smooth function with compact support, or then it equal to minus e to the 5 and d over dz e minus phi alpha. So how I can come up with these formulas? Because given these operators and given this inner product, I can ask for formal adjoint operator. So this is nothing but the formal adjoint of the operator d over d bar with respect to the inner product. We will check it. Maybe that exercise, right? Anyway, that exercise to checking this. Okay, let's come here. Good. So now you see, when you apply so consider the equations. The equations du over d f. But remember, we already talk about the weak sense. Okay. Consider this equation apply to the special ones, alpha e to the minus phi, instead of just alpha. This still smooth function with compact support, because this guy smooth function with compact support. So multiply with any smooth function gives you the same. And omit. Remember, we will, because this the lambda will appear everywhere. So to save writing, so omit in writing, okay? To see more compact way of the formulas. So you get that omega, if you act on this one, and you get that is u, d star phi, let me write it first, alpha bar e minus phi will be equal to f alpha bar e to minus phi. So just look at this one. If you apply, because this is explanation of equation in the quick sense, okay? So if you write it down, this guy, so this guy is nothing but by definition is e to the minus phi, e to phi minus here, right? This right, and d over dz of e minus 5 of alpha. But this have two factors will equal to hit to this one, then you get minus come out and cancel, and d over d, am I right? Okay, so this one equal to this, sorry. This one equal to this. And if you take bar, then bar will come here, right? So if you take a bar here, then because of this real value function, then bar will come here and come here. Okay, and multiply with this factor, then this will cancel. So you get actually this f act on the same one. Okay, so if you consider this function apply to this one in the quicksand, then it gives you this one. Okay, so it's not hard to see this fact. Then the following key propositions tell you how to solve the Debye equations in the weak sense in one dimension, and also have a version in high dimension like this. So this one is the key. So let f belong to L2 this weight minus. Then it says that there exists solutions, of course, in Greek sense. To the equations satisfying not what we want, that the L2 norms omega is less than a constant. Remember, we reformulate our conjectures so that we have L2 estimate, and this is a statement, at least in the weak sense, right? If and only if. The following inequality holds that omega of f alpha bar e to minus phi, that's why we apply to this guy instead of alpha, absolute values will be less than the same constant 0 here, multiply with the integrals of form joy act on alpha take square e to minus phi. Okay, and this will hold for every alpha smooth functions or test functions with compact support. for every yes. So in other words, to solve our problems, you need to prove an inequality. So you reduce the solvability of the Debye equation to prove one inequalities. Proof. So there are two directions, if and only if. Of course, if you have the solving equations, so say for instance for necessary conditions, conditions, I mean only if is easy because you can use Cauchy-Schwarz inequalities. Suppose we have this inequality, okay? So let's write it 2, say, and this will be maybe 3 star, maybe just write 3. So suppose we have this one is 2, number 2. So remember we have this one is equation number 2. When you apply two sides with the same thing, you get this identity. Now by equation 2. So by 2, we know that f alpha bar will equal to u, the form of joint alpha take bar e to minus 5. So this one appear, and this guy appear, right? And now if you look carefully, then you can use Cauchy-Schwarz with the measure is this guy. And by Cauchy-Schwarz inequalities, it take absolute values. Then you get that it equal to or less than equal to the norm of u square with respect to this measure and multiply with the norm of conjugate of formal joint of alpha square with respect to this measure. And this guy, by assumption, is C0. So which means that we imply this inequality hold for every compact support function alpha, just simply by the identities and the Cauchy-Schwarz inequality. So we get one direction quite easy. And for the others, we need a bit more about functional analysis. So I can iterate this one. Okay, so we have this inequality. So now for it, so it implies 3. Okay. Now suppose we have 3, which means that the inequality 3 holds for every compact support alpha. How can we get that? We get not only one solutions in the weak sense, du over dz bar equal to z equal to f, but with also the estimate that the L2 norm is the control. Okay, so now to prove the inverse, you denote the following space E, the subspace. I mean, this suggests that all of this guy for alpha is compact support in. So one of the remarks that these operators minus e to phi d over dz of two factors is e to minus phi alpha. So you can express it out. Then this is a linear operator. in terms of alpha when you change alpha. Do you agree? No, it's Z. Because it's formal joint of D of G bar, it should G. Formal joint of D over G bar. So this is DC, okay? As I said, because you need to take bar here, send bar appear here and bar appear here. So, good. This is linear operators. Note that and this one, of course, is subspace of because it's compact support, and this is all of the integrable function with, I mean, on any compact set. Okay, so it's subspace, linear subspace. Because of this is linear guy. Okay, so once you have a linear subspace in some Hilbert space, so what success used to use is the Hahn-Banach theorem if you define the right linear operators. So define linear functional on E, because we want to extend it by L from E, functional in the complex values, where L act on the bar star phi of alpha, then equal to very, I mean, you have already what is formulas, just equal to F bar E to the minus phi. Of this, just take conjugations, this one. The reason we will come later because, okay, so take conjugation of this one, the real values, and this just go to F bar, and this alpha bar is alpha, just for convenience. Okay. Then using the inequality 3, what is inequality 3 here? Tell you that our linear operators, our functionals is bounded functional in the Hilbert space, which is equivalent to say that it's continuous functional on linear subspace. And by Hahn-Banach theorems, so by 3, let me write it, we know that L is well defined on E. Right? Because, I mean, the value is finite. And not only that, and its norm is at most right, because this is 0, and the norm is just take suffix of all of this, divide by this, and take square root, it's just square root of C0. Good. So now we use the basic theorem in functional analysis. So by Hahn-Banach theorems, then imply that L's can be extended to all space with the norm at most the same, with the same norm, or the norm is bounded by square root of C. So have you heard about the Hahn-Banach theorem? Maybe first year students have not taken the course. but I mean the 4 years should have taken the function analysis course. And this is one of the basic theorem in function analysis. Okay. So it's very good exercise if you can show that, okay, in our finite linear subspace, say R2, give you any functional or continuous function on that, you can extend to be a linear function on the larger space. But the powerful of this one is hold for any Banach space or norm space. Anyway, but one of the requirements is you need to control a norm, and here we have control of the norm. Otherwise, it's not true. Okay, so we have the extend our linear functionals to the whole space. So how can we verify same norm such that okay, same norm. So now use the fact that this one not only Banach space but it's Hilbert space. So now you can use the Riest functional Riest representation theorem again. Okay, now you can find. Okay, so erase this. So by Riest representations theorem, because any functional on Hilbert space have one of the, representation point, and by Riest theorems, there exists unique U in this space, such that, with a norm is at most such that our functional have a representation formulas, and this holds for any Z in our space. So you use second time the Riest representation theorem and choose Z, very simple. What you already knows. Because this is an element in this space. Okay, and what gives you is what? Then we have the identity number 2. That D bar star 5 alpha U bar E minus 5. This one just plugging this, okay, equal to F bar alpha E to the minus 5. Remember the value of these functionals on this space, because this belongs to E. And the value is we know with the right hand side. So if you plug the value, the element G here, then you know the value. But we know that this have this formula. So for particular Z, you get this equal to this. But this is nothing but the identity explain the which solutions of equations. If you write equivalent to say that for every this one, or equivalently, take conjugation. So U alpha bar, this one bar equal to F alpha bar which identity 2, or equivalent to that. Okay. I mean alpha and alpha e2 minus is no different. Just matter of writing extra this factor. Because you just replace alpha with this, still compact support. But you gain something. Next. Okay, so we prove the propositions which reduce the solubility of the Debye equation with L2 estimate. This L2 estimate here. The norm is this to inequalities. Okay, so how to get that inequalities? So by the way, any question for the proof or statement? So it's okay, right? To good. So now let me recall what is the basic inequality we want. Okay, so yeah. So the inequality 3 asks you to show that f alpha bar e to the minus square is less than C0 omega the phi alpha e to minus phi for any alpha in our compact support. So this is the inequality we are after. Okay. So everything comes to these inequalities. So now you can see why we introduce the weight. Because what so far we haven't seen why we use the weight, right? And the weight gives you the extra factors in the following so-called basic identities to help to gain this inequality. So propositions. And this is Hochmander's. But why introduce identity? Okay, so now it holds for any smooth. Okay, so let phi is the SPO. So let alpha is test functions, then Laplace of phi square, okay, plus with say omega square e to minus phi and equal to omega alpha square e to minus phi. So why do we call this is basic identity? Because you want to have an estimate on f. Okay, so you see this factor up here, right? So this is a positive one. Okay, so which means that if you get rid of this factor, then you get that this one will be less than this one. Okay, so if you can relate this one to f, then we are done, right? Maybe I will not prove this one. just give you why we can relate this one to f. Okay. So I'm sorry, I think I say something wrong. So this one is not needed. We will use this one because so I will not prove this. I just use this identity. Okay, this purely computation, direct computation. If you are strong enough, then you can verify it. And just remark that we have two terms, this term and this term. And this term, because of our assumption is positive. And we make the Cauchy-Schwarz inequality because one of the things here, you will see. We want to estimate this guy. Okay. So you see this alpha, this f. So by a brave application of Cauchy-Schwarz inequalities, you just get this guy, square okay, you plug the Laplace because it's positive guy, and okay, you see what's going on here. You have this one, and this one you know that it's bounded. It's C0. This is C0. Okay, then of course you verify the inequalities. So let me state our theorem is just simply the detailed statement of that trick. Theorem 4.4. So suppose that you have again our assumption that positive f is given in our space. Then there exists a solutions u to the equations f okay, then there exists satisfying that okay. So what is great about the statement? The right hand side is verified, given. All depends just on the given data. So f functions the norm. So this is known. Given f, then this is what the known function as number. Then it states that, okay, given f and 5, you can find a solution to solve this equation in quicksand so that L2 norm is controlled by this number. So technically our solution is solved. So after choosing this weight, you can modify this C0 so that it's optimal. Okay. Okay, so that is the the solution of the pi equation in the weak sense. There's another theory, so-called the regulative theory, asks you to whether if f smooth, you can upgrade the solution to be smooth. So indeed, it's true, but there's another thing about regulative theory of the PDE. Okay, so I will not prove this one either, because just explain this trick. If you spend maybe 30 minutes or 50 minutes, then you can derive from this trick, combined with basic identities and the basic inequalities to get the proof. Okay, so in 10 minutes, let me just mention one important corollary is that, okay, you solve the equations, then you ask what is the best solution. Okay, and the best one will be orthogonal with all of the others one of space. And that it belongs to one of the exercise. So when you solve the, so questions remain, arise, what is the best? And the one turns out to be the so-called the minimal. It is called minimal solution. Which means that it is chosen so that it is perpendicular to our very well, at least at the moment, is familiar with us, holomorphic one. Now, or equivalent to say that the inner product so this we have to show that this closed subspace. So any other element here you can project to this subspace, right? And that unique projections from you get is minimal solutions, which is equivalent to say that it's orthogonal. So this is our space, and then any element here you project, and you get this one, because you need it require holomorphic. So yes, okay. So in maybe 7 minutes, that is all about the one-dimension case. So what I want is that this is just beginning, and there's a rich theories in dimension 2 and higher. So the last sections, very quickly. High dimensions. So you can maybe define all of the what we have done so far. For omega now is just Cn, but for simplicity I just take n equal to 2, which can write in coordinate G and W. G is one complex variable, W another complex variable, and omega to be about the subset in this one. Okay, a function can be defined, can be holomorphic in this in two variables if separately, which means that when you fix G, then this holomorphic in W. When you fix W, holomorphic in Z. Okay, and it have all the equivalent, say that you get now 2 equations instead of 1 equations. Okay. Then you can also have a general the Cauchy formulas in 2 dimensions, a complex dimension 2. For continuous. So now you, instead of you have this, you go by this or poly this in generals. So if you know d of r of g0, a point now is 2 complex coordinate. Okay. Then just repeat. I mean, this is nothing but the set, say in C2, you go by this, and in general, you go polydisk. You will have one talk about this on tomorrow. Okay, then the Cauchy formulas also have the same statement. But instead of looking at the boundary of this one, it only affects the so-called distinguished boundary, which means that on quite strange, right? But when you prove, you see it not strange. On this one, you have that for any point in that by this, then it will equal to 1 over. Just a bit hints. Now you take it square. And R2 W0. And now you have 2 variables, f of zeta, eta, and zeta minus z, eta minus w, d, eta. So this is a line integral in both variables. You just interpret it. Okay, so you also can define Bergman kernels in the same way. Okay, and let me just and also you can generalize what is subharmonic functions, which means that now in 2 variables, then you restrict on x complex line, it is subharmonic. So it's called the pure subharmonic function. So let me just summarize very quickly what is going on from R1 to n dimensions. And still very active research areas. So n equal to 1 and general. So n equal to 2. So we have holomorphic. We also have homomorphic here. Just define over there. You have subharmonic. Now you have a so-called pluri-subharmonic, meaning that restrict on any complex line is harmonic or subharmonic, because this one is just 1-dimensional complex 1-dimensional. And you have what is green functions. So now you have similar, you so-called purely green functions. You remember one of the characterization we take is take suffix over negative subharmonic functions with the value in negative, right? For green function, then you can define similar here. Take suffimum of all pluri-subharmonic function which is negative in the domain, right? And of course this EOZ, the mean object, so-called very huge subject called d-bar equations. Okay, that's it. Thank you for your attention.